Okay, thank you very much. So thanks a lot for putting up this nice workshop. I've enjoyed the talks I could follow this week so far, and I'm sorry I couldn't make it to Bangalore. I hope to be able to make it next time. So I will discuss today some work we've done over the last 4 years, say, on the thermal properties of frustrated quantum magnets. This is almost an oxymoron because it's well known that frustrated quantum magnets suffer from a very severe minus sign problem in quantum Monte Carlo. And the idea to study theoretically their thermal properties at very low temperature, looking for phase transitions, is almost impossible. I mean, I myself never thought it would be possible to do some of the calculations I'm going to report today on frustrated magnets at low temperature. These are rather recent developments. And these developments go along two lines. And well, first of all, let me thank all the collaborators that have participated to this project, a number of theorists. And about quantum Monte Carlo, the most important persons are Stefan Wessel and Andreas Honecker. And a lot of the discussion and interpretation has also been done with Bruce Normand. And about IPEPs, of course, I have benefited from collaborations with Philippe Corbeau and postdoc in Lausanne, Olivier Gauthier. And some of the results we've found have had a nice experimental realization, and that was done by Henrik Ronov, Christian Rueg, and their group. So what the scope is going to be in the following, I'm going to discuss mostly two methods. Go back to quantum Monte Carlo and review why there is a minus sign and why, under certain circumstances, even for frustrated magnets, it's possible to go around the minus sign. And this will be true for some model systems, toy models like the fully frustrated bilayer, but kind of more, maybe more interestingly or less obviously, it is also true to a certain extent for the Shastry-Sutherland model, which is a model of physical relevance. Then I will turn to another approach, which is complementary, and which is a tensor network-based method to calculate thermal properties. And this allows to study the Shastry-Sutherland model in a parameter range where it is relevant for famous compounds, strontium copper borate under pressure, and I will review the properties with there. And then I will finish with another project done with IPEPs, showing that IPEPs is really a versatile technique, and we've studied the J1, J2 model in the square lattice and found evidence of an Ising transition. So let me start by a very quick review of quantum Monte Carlo and why there is a problem with the sign. So the partition, quantum Monte Carlo starts from representing the partition function as a path integral. The starting point is that the partition function is the trace, but to calculate the trace of exponential minus beta h, one should diagonalize h, and of course, this is in general not possible. So one needs to find ways around this problem, and the way proposed by quantum Monte Carlo is to split the exponential into a number of smaller exponentials and to introduce the closure relation at several steps between these. And then if delta tau is small enough, that is, if we make a number of slices large enough, L is large enough for a given temperature, one can expand the exponential, and the matrix elements that enter are just 1 minus delta tau h up to order delta tau square. And now comes the following remark. It will be possible to probe easily this partition function if all matrix elements are positive. And this will be the case if the matrix element between states that are orthogonal in the closure relation are such that this is positive. So this means that if the matrix element of the Hamiltonian is negative, that is, there is possibility to write the partition function of a quantum problem with only positive signs and make some important sampling using Monte Carlo, provided all off-diagonal matrix elements of the Hamiltonian are negative or zero. So the minus sign comes when the off-diagonal matrix elements are positive. This is a source of some confusion. And then in that case, one can write the partition function and can any observable in terms of make a sampling of the observable. And there is no minus sign. It's really like sampling a classical problem and then Monte Carlo simulations are possible. Now, the problem is that for quantum magnets, this is rarely possible. For instance, if one writes the Heisenberg model, the antiferromagnetic Heisenberg model in the configuration basis, all off-diagonal matrix elements are positive. So we are in a situation where there is in principle an extremely severe minus sign. Now, this can be overcome, and this has been realized early on in the 80s, if the lattice is bipetite, because then by making a rotation by pi on one sublattice, one is able to change the off-diagonal matrix, the sign of all off-diagonal matrix elements in the Hamiltonian. So they were all positive, they all become negative, and there is no problem. And this is why the Heisenberg model on the square lattice, for instance, has been solved numerically with the quantum Monte Carlo. And in the late 80s, it was proven that there is long-range order based on such simulations. But if the lattice is non-bipetite and we have an antiferromagnetic Heisenberg model, there is no way out. There is no way to reformulate the problem with only negative off-diagonal matrix elements. And it turns out that this is not just a small problem. This is a very serious problem. The error bars of the simulation, that it's still possible to do simulations, but the error bars become larger than the signal at temperatures of order the coupling constant. So there is no way to study the low temperature properties of frustrated quantum magnets in this way. So that's the basic problem, and this is why very little has been attempted with quantum Monte Carlo for frustrated magnets. It's well known since the late 80s or early 90s that this is basically impossible. Now, if we move to frustrated model, it turns out that in some circumstances, it is possible to do simulations, but one has to change basis. And the basic idea is the following. I first illustrate it in the case of a ladder. Let's consider a system with a Heisenberg model. So we have antiferromagnetic bonds, red, blue, and green. And let's suppose that the cross-coupling JX here, or J cross, is equal to the parallel coupling. If they are strictly equal, then the Hamiltonian can be reformulated in terms of the total spin on each dimer. This is called T here, because this spin is coupled to that spin and that spin with the same equal coupling when Jx is equal to J parallel, so that the Hamiltonian is just a Heisenberg model for the total spin of each rank. And the rank coupling can also be written in terms of T. So in that case, the Hamiltonian can be, in the dimer basis, can be entirely rewritten in terms of the total spin. So this leads to an idea how one could perform quantum Monte Carlo simulations on this problem. And this relies on looking at the Hamiltonian in dimer basis instead of the configuration basis. So in general, this Hamiltonian will involve both the sum and the difference of spins on a dimer, but if there is full frustration, as we say, that is, if each spin is coupled to both spins on a dimer, then one can write the Hamiltonian in terms of the sum only. It's a spin model. It doesn't mean that quantum Monte Carlo is possible, but then if the dimers live on a lattice that is bipetite, then we're back to the original problem. We have a collection of Heisenberg models because the total spin could get different values, but each of these Heisenberg models is such that the off-diagonal matrix elements can be negative. So it means that for some fully frustrated systems, it is possible to do quantum Monte Carlo simulations completely free of any minus sign. I think this was not really recognized. So there was some precursor works done on the one-dimensional system years ago, but this was not fully recognized until some work by Stefan Wessel and his student John Stabsman that is shown here. So in one dimension, for the fully frustrated ladder, we could do quantum Monte Carlo, but in one dimension, we do not expect any phase transition, so there is no real interest in going to low temperature. But then if we move to two dimension, this is another story, because in two dimension, we can have some interesting physical property. So the model we've looked at is a generalization of the fully frustrated ladder. We have dimers. These dimers are arranged not just in a ladder like this, but they are arranged there is a two-dimensional plane of these ladders. And if the cross coupling is equal to the parallel coupling between the dimers along this line, we are again in a situation where the Hamiltonian can be written entirely in terms of the total spin of each rank, that of each dimer here, vertical dimer. And then in the along this axis, we thus expect to be able to do quantum Monte Carlo. And it turns out that the ground state is very simple along this axis, because if the coupling here, the horizontal axis is the ratio of this coupling perpendicular to the inter-dimer coupling. If this coupling is very large, we expect to make dimers here. And this is an exact wave function, because the coupling between the singlets are just zero. The total spin is zero. And it turns out that this is the ground state down to a certain value. And at that point, there is a first order transition to a state where all dimers are spin 1. So we have at 0 temperature in that system a phase transition between the dimer singlets, where all the dimers are in singlet state, and a square lattice antiferro magnet with a spin 1 at each side, because then these spins form a spin 1 on each time. So this is the 0 temperature phase diagram. And since we can do quantum Monte Carlo, this was the ideas tried by Stefan Wessel and his student. And it turns out that the physics is really interesting at finite temperature. Why? Well, if you think of it, we have at 0 temperature a first order transition between two states. If we so this means that there is a level crossing between the ground state energies. If we increase the temperature, we expect the transition to remain first order for a while, and the line of first order transition is going to be signaled by a crossing of the free energy, no longer the energy. And see, there is a strong crossing in the energy. We expect this to be true for a while, to remain true until a certain temperature. And when and at this temperature, when the order parameter, that would be, say, the value of S dot S, which jumps at the transition, S dot S on the dimer, it jumps here at the transition from being a triplet to a singlet. When this jump goes to 0, we expect to have a critical point. And this critical point, since we have only two states in competition along the line, this critical point is expected to be in the Ising universality class. And this is exactly what we found with quantum Monte Carlo. For these systems, a fully frustrated system, we've been able to map out the phase diagram at finite temperature and to identify a critical point. And the critical point, so if we sit at this line is not fully vertical, but on that scale, nearly vertical. So if we sit at the estimated value of the coupling where this critical point sit, and if we look at the specific heat as a function of temperature for different sizes, the specific heat increases logarithmically with the size. And this is the typical scaling you expect for the two-dimensional Ising model, where the exponent alpha is equal to 0. So it is possible, and this is the rather recent results. It is possible under certain circumstances to do quantum Monte Carlo for a quantum system. And of course, the next idea is to try and look for experimental realization of this. We don't know of a bilayer, but we know of a system, strontium copper borate, that shares some of the properties of the bilayer system. This system will be discussed at length in the next talk by Philippe Corbeau. I will just give the introduction needed to understand what I want to say. So this system is made of orthogonal dimers of copper here in red. Copper is 2+, so it's a spin 1/2. For that particular system, the ratio of the inter-dimer coupling to the dimer coupling is about 0.63. It's an orthogonal dimer model. It has a gap, so the system is going to be in a singlet phase. And this was shown by these experiments. They also revealed other anomalies and plateaus. This is why the system was famous in the first place, but this is not what I want to discuss today. I want to discuss really the properties in zero field of the model. This model is known as the Shastry-Sutherland model because by pulling, we can end up with a square lattice with some diagonal coupling that was introduced in 1981 by Shastry and Sutherland as a model where we have a product of dimers. And the connection between this model and the fully frustrated model is the following. If we look at the Shastry-Sutherland model here with the black and the blue lines, and if we introduced a next nearest neighbor coupling J2 to the system, then when J2 is equal to the interdimer coupling, we are back exactly to the same, it's topologically equivalent to the fully frustrated bilayer. So here, if we have J2 equal 1, we have the fully frustrated bilayer. If J2 equals 0, we have the Shastry-Sutherland model. And as we increase the interdimer coupling, we have the whole phase here where the ground state is just a product of dimer singlets. So we have we have a clear analogy between this phase here and the dimer phase of the fully frustrated bilayer. And when we increase further the coupling, we have a first order transition to a spin 1 antiferromagnet for the fully frustrated bilayer. We have a first order transition to another phase for the Shastry-Sutherland, but we still have a first order transition. So maybe this system could be an experimental realization of something very similar to what we found in the fully frustrated bilayer. So we were, that's an interesting remark. And the problem now is to know whether and under which conditions we can actually calculate and study the thermal properties of the Shastry-Sutherland model. Well, the bad news is that although the ground state is a product of singlet dimers, the Hamiltonian cannot be written in terms of the sum of spins of the dimers, because some dimer, and unless J2 is equal to J1, some dimers are coupled only to one spin of neighboring dimers, so we cannot write the Hamiltonian in the sum, and this means that quite generally, we're back to the sign problem. That is, if we try to calculate and estimate the way it is done in Monte Carlo, is to use a probability which is always positive, but then there is a sign. And the actual expectation value of an observable is the expectation value of this observable in this positive probability of the sign of this times A. But we have to divide by the expectation value of the sign. And the minus sign problems comes into play when the sign becomes very small. And this typically occurs when the temperature is of the order of the coupling constant. So we're back to a problem, but it turns out that for the Shastry-Sutherland, this is not always a killing problem. And that's again a big surprise that it is possible, even when there is a minus sign under certain circumstances, to do quantum Monte Carlo. It turns out here that up to a ratio J over JD of 0.526, etc., there is a numerically exact result for that. It is possible to do Monte Carlo because the model that would be probed with this, that is the model that will have all off-diagonal matrix elements that are put arbitrarily negative, this model had the same ground state as the physical model. So there will be a minus sign, but it's easy to show that under these circumstances, the average value of the sign goes back to 1 when the temperature goes to 0, because the ground state is the same. So this means that there will be a sign, but at low temperature, the sign is not a problem. So quantum Monte Carlo is in principle possible again. So quantum Monte Carlo is really, is not always impossible. So this is shown here. We calculate the average sign for different ratio. And if you take ratios, as long as the ratio is smaller than 0.52 something, you see that the sign is not equal to 1, but it goes to a value which is moderate. And then it goes back exactly to 1. And it will reach a value, if we approach the value 0.526, it's going to become very small. And then simulations in this temperature range will have to be long to have small error bars, but ultimately it goes back to 1. But if we go like 0.6, this is quantum Monte Carlo facing a minus sign problem. It goes to 0, remains equal to 0, and then the error bars of the signal get very big. So quantum Monte Carlo can be used for the Shastry-Sutherland model, but only up to a certain ratio. When in that case, it works very well. That is, we do quantum Monte Carlo, we can do on 32 sites, 200 sites. It makes no difference. The results are essentially converged at the function of this size, and this is for a ratio 0.5. Unfortunately, if we look at the phase diagram of the, I should go back maybe to this. If we look at the phase diagram of the Shastry-Sutherland model here, the interesting physics does not take doesn't take place below 0.52. It takes place rather in the range 0.6 something. So we have a problem. If we want to find to investigate the physics of this first order transition in the Shastry-Sutherland model, we have to go to another method. So this is where tensor network starts. You have had a presentation, a tutorial by Philippe Corbeau about tensor networks. So for those of you who followed it, this is going to be a repetition, and I'm going to be very quick. A tensor network is the method to represent wave function as a contraction of a tensor network. And in one dimension, DMRG can be reformulated in that way, where the tensor are just matrices. But in 2D, the tensor will have a rank, which is the number of neighbors coupled to the site plus a physical index. But it turns out to be, it has been proved somehow empirically to be a good way to represent the wave function by only taking a finite bond dimension for the tensor. And there are some reasons for that have been explained by Philippe Corbeau. I'm sure that it has to do with it's derived from quantum information. It has to do with the fact that the states that are represented by these tensor networks have the area law for the entanglement entropy, which is believed to be the case for a Hamiltonian with local couplings, at least for gapped Hamiltonian. Now, I suppose Philippe must have also mentioned this, but tensor networks can also be used at finite temperature. And this is again a method of quantum information using the concept of a purified state. One will, to each degree of freedom, one can attach an ancilla degree of freedom, and consider the full system. And if one makes, for instance, singlets between the physical degree of freedom and the ancilla, this will represent and trace over the ancilla degrees of freedom. This means that one traces over all configuration of the spin system. So this corresponds to infinite temperature. And then starting from this system and letting this object evolve in imaginary time up to a certain temperature, but according only to the physical Hamiltonian, and then tracing over the ancilla degrees of freedom, one gets a faithful representation of the density operator, or the density matrix of the system. And this was proposed in 2004, but it wasn't really developed until more recently, where there were a number of papers, including some of them including Philippe Corbeau, but otherwise by the Polish group, Piotr Czarnik and Jacek Dziamarga, who put this into work and showed that it is actually possible to do some simulations for this. So this means that there is an alternative to quantum Monte Carlo, and whether it works or not for frustrated quantum magnets, whether it is accurate has to be checked by looking at actual case. And it turns out that for the Shastry-Sutherland model, it works very well. So we have benchmark. We can use now quantum Monte Carlo as a benchmark for the thermal properties of the Shastry-Sutherland for ratios that are smaller than 0.526. So if we take a ratio 0.5, quantum Monte Carlo simulations are represented here with these arrow bars, and this is the specific heat. And the IPEPS data obtained for bond dimension 16 are shown at the blue line, and they are basically indistinguishable. So IPEPS with a moderate bond dimension, that is a bond dimension that one can simulate in a finite time, seem to be very accurate. And then if we move to larger ratios, because this is our goal, you see that the sign problem in quantum Monte Carlo shows up here in error bars that become very large, and there is no way to understand what's happening at low temperature with quantum Monte Carlo. But IPEPS continue to have a very well-defined specific heat. There is a big peak growing, a double peak structure developing at 0.6. And this means that in principle, we have now at hand a method that should allow us to study the thermal properties beyond the value 0.5. So this is, let's go back to the system. There is a phase transition here around 0.6 something for the Shastry-Sutherland model at zero temperature between the dimer phase and another phase, a plaquette phase. I suppose Philippe will show more details, but let me show this phase diagram because it's important for our purpose. In fact, the first order transition has been determined by zero temperature IPEPS to be at a ratio 0.675. So if we want to study the equivalent of the critical point, we have to do simulations in a range going over this value. And this is what has been attempted by Philippe Corbeau using IPEPs. And the result is exactly what we were hoping for. There is a critical point in that system. So there are some for technical problems, it's not possible to go to extremely low temperature, but please look at this scale. This is already extremely low. We're talking about the temperature, which is the coupling, the basic coupling divided by 20 here. So it is already very low temperature. And looking at the specific heat over T, as in the plane of temperature and coupling constant, there is clearly a maximum here. The maximum can be shown to be consistent with an Ising transition. And the physics of this point is really that of a critical point terminating a first order transition, as shown here. The spin-spin coupling on a dimer is actually jumping across this line that terminates here from being very negative to being about zero. So there is a jump, and the jump goes to zero at that point. At that point, the correlation length, as measured by the tensor, by IPEPs, by the transfer matrix eigenvalues, is also diverging at that point. So we have evidence of a critical point in that system. In the Shastry-Sutherland, as in the fully frustrated bilayer, we believe that there is a critical point. What is the physical? Now, what is on the experimental side? I'm telling the story, the things happen more or less in parallel. I'm not telling the story exactly in the way it happened, but I think it's clear here. Now, what about experiments on strontium copper borate? Can we probe this with strontium copper borate under pressure? The thing to go over this phase transition, we have to change the ratio J over JD. And the natural way to try is to put pressure. Frankly, a priori, it could go in both directions, increasing or decreasing the ratio. It turns out that it does increase the ratio. So taking the strontium copper borate, which has a ratio 0.63, and putting pressure will increase the ratio. And there is a number of experimental work, starting from a work by Takigawa and collaborators in 2007, showing that indeed pressure is able to drive the system into another phase. I will flash this, maybe Philippe will show this, but I think I'm running kind of slowly out of time. So these NMR experiments revealed that there is something happening with apparently two copper sites. So it's not the understanding of the intermediate phase in strontium copper borate is a little bit tricky, but there are many experiments revealing that something happens around 2 kilobar. These are measurements that the signal here is something like the second derivative of the magnetization, and again something very dramatic occurs. There are some neutron scattering showing that again around 2 kilobars there is a phase transition in the system. They suggested that the ground state is actually not the plaquette phase of the Shastry-Sutherland, but another one. But it's a first order transition anyway, which is the most important thing for our purpose. There are some IISER data also showing something happening. And then there was this very interesting paper by a Chinese group and Anders Sandvik, who measured the specific heat and showed that there is a maximum of the specific heat. And then here, there is a transition temperature around 2 Kelvin that they interpreted as the transition entering the plaquette phase. So here we have a first order transition. And if we increase, so in fact, it's probably more like 18. If we increase the temperature, we expect to keep a first order transition. Then we have this transition at 2 Kelvin. And it could be that this transition connects here. But in fact, this is not what the experiment reveals. And here they had only some pressures and it wasn't clear. So there is a small peak here interpreted as this Ising transition here. And these peaks look like a broad peak. But in fact, looking at the data now, Henry Chrono had very similar data with colleagues, but they were looking at slightly different pressures. And looking at this data, one realizes that around 18 to 20 kilobars, this broad peak becomes actually very narrow. And if we make a color plot of the specific heat divided by the temperature here, there is evidence of a maximum here, but not at a temperature consistent with the 2 Kelvin transition to the dimer phase, but isolated in the temperature range. And now going back to the results of Philippe Corbeau, this is clearly the natural interpretation is that there is indeed a critical point at finite temperature terminating the first order transition that starts here between the dimer phase and the plaquette phase. So that's the interpretation of our result, that we have a critical point terminating a first order transition in an actual system, which is, well, from the point of view of universality, this is actually present in many contexts. Was first, actually, the concept of a critical point was first discovered 2 centuries ago in 1822 by Cagnard de la Tour when he studied liquids, and in particular water, when he showed that there is a point above which there is no longer a first order transition, but one can go continuously from gas to liquid around this critical point. But it's present in our model. It's present in the fully frustrated bilayer, as I showed, but it's also present in the Ising model in a field. This is very similar. If we look at the specific heat, it will always have this behavior. So we have a maximum, and then suddenly at certain point, isolated in the TH or TP diagram, it will be an isolated point where the specific heat diverges. And this is typical of a critical point. So IPEPs turned out to be extremely useful. We would not have been able to identify the critical point of the Shastry-Sutherland if it was only for QMC. Now, finally, in the few minutes, last minutes, I will discuss the last work we did on that, on the J1, J2 model on the square lattice. Now that we're confident that IPEPs can do the job to find low temperature phase transition, let's look at some models where we believe there should be such a phase transition and see if we can do it. And one very simple example is the J1, J2 model on the square lattice, where we have nearest neighbor and next nearest neighbor. The classical phase diagram was worked out by Chandra and Dussault in 1988. Without J2, of alpha is a ratio. So if alpha is small, we have Néel order. If alpha is very large, we have 2 sublattices that are Néel ordered and that can classically rotate around each other, but quantum fluctuations will leave the degeneracy, and the ground state in that region here is expected twofold degenerate with 2 helical states with wave vector 0 pi or pi 0, and in between a spin liquid. So in that phase, it was predicted in 1990 by Chandra, Coleman, and Larkin that there should be a phase transition at finite temperature. It's a Heisenberg model, so magnetic ordering will not occur at finite temperature because of Mermin-Wagner theorem, but the fact that we have 2 helices defines an effective Ising order parameter, depending on which helix is chosen, and they should be an Ising transition, and they made a prediction. They had a prediction for the behavior of the critical temperature at very large values of J2, close to J2 equal 1/2, it wasn't clear. And but this prediction was impossible to check it for quantum spin so far, because there is the quantum Monte Carlo is really unable to do the job there. So we decided to try IPEPs. It was trickier than we hoped, because the standard algorithm has some pitfalls. In particular, they are, if one doesn't implement SU2 symmetry during the imaginary time evolution, one has some artifacts where the SU2 symmetry is broken at finite temperature. This is an artifact of the simulation, and one has really to fight against this to be able to avoid this artifact, because this artifact in most cases occurs above the physical transition. But once this has been done, then it was possible to actually do simulations and identify an Ising transition. This is shown here. So these are data for ratio J2 over J1 equals 0.85. That is clearly above the in the collinear phase, where we have 2 helical states. And the energy calculated, chi is a parameter for the CTM corner transfix renormalization group. The corner transfer matrix is a way to actually contract the tensor, so it has itself some control parameter chi, and here the results are already very little dependent on chi. So the largest value of chi we could do is 256 for the experts. So there is clearly an anomaly in the energy. And if we calculate the specific heat, what we found is that there is a broad maximum at the temperature of the order of the coupling constant, as in any quantum antiferromagnet. And then at lower temperature, there is a very clear peak in the specific heat, a divergence of the specific heat. And there is also an order parameter when some kind of, when the system has chosen in which direction to make the order, and this order parameter has a scaling that is consistent with the exponent beta equal 0.125, that is 1/8, which is typical of the Ising transition. So this transition, there is a phase transition, and as far as we can say, it is fully consistent with the Ising universality class. Important for us was also to check how this critical temperature change with temperature. So here are some data for different values of the bond dimension. So they are a little bit scattered, but they build a curve that is very clear. If we look at the critical temperature of the function divided by J1, it seems to go to 0 at a value which is above 0.5, consistent with the expectation that the helical or collinear phase only develops for values of around 0.6, but maybe it even goes, if it goes to 0.6, it's linear. So the scaling here is it would be linear. But more importantly, for our purpose of checking that this is really the phase transition predicted by Chandra, Coleman, and Larkin, we looked at higher values of J2, because Chandra, Coleman, and Larkin approach is really a large J2 approach, small J1, and they predicted that the TC in units of J2 should decrease logarithmically. And we see really that the TC goes over a maximum, and the data here are consistent. Of course, we don't have enough precision to fully identify this, but this is consistent with a critical temperature going to 0 at very large J2 logarithmically. So really there is ample evidence that these results are fully consistent and that Chandra, Coleman, and Larkin prediction of a critical temperature raising logarithmically from 0 upon increasing the coupling between the J1 between the two sublattices is realized. And so that this transition that we have captured is the physical transition. And look at the critical temperature. They are not at all of the order of the coupling constant. They are really about 10% or even less of the coupling constant. So this is a region which is only accessible, I believe, to these simulations. So I think I'm slightly over time, so let me conclude now. The main conclusion is that thermal properties of frustrating quantum magnets are no longer inaccessible. I write it this way because, of course, it's not like you give me a model and I can do simulations right away. This is not that simple. IPEPs are very much lattice specific, but at least now we have opened, I think, a window onto this world of the low temperature properties of frustrated quantum magnets with possibly a lot of phase transition. Quantum Monte Carlo, I must say, much to my surprise, is really sometimes possible for frustrated magnets and can give a lot of insight. IPEPs is also very powerful. We've been able to identify thermal Ising transitions and the critical point in J1, J2, and Shastry-Sutherland models. So we are now working on other problems where we expect finite temperature properties to be relevant. To the extent some extensions, I mean, Quantum Monte Carlo, it's still in general plagued by a minus sign problem, but there are ways around it. And not only by finding a basis where there is absolutely no minus sign, but also by finding a basis where the ground state can be the same if we put all signs, all of an diagonal matrix element to be negative. That is, even if there is a minus sign, under some circumstances, it is possible to do Quantum Monte Carlo. We found other examples, so one should keep this in mind and really think if one faced with a problem for thermal properties to really try Quantum Monte Carlo. IPEPs will be useful, and I think something that would be very useful now in view of all the neutron scattering data that have been collected over the years at finite temperature. It would be really interesting to see if one can combine real-time and imaginary time evolution to be able to calculate the temperature dependence, for instance, of the spectral function in quantum magnets. And with this, I will stop and thank you for your attention.
Thank you very much. The presentation is open for discussion now. Are there questions? Yes, please. Yeah, just speak.
Hello.
It's okay. Yes.
Okay. So my question is, in the Shastry model, why the Hamiltonian cannot be written in terms of the sum of spins of dimers?
Yeah, that's okay. Maybe I was obviously too fast on this. Let me go back to it and just look at the. I think it's enough to look at the topology of the system to understand this. You know, if you look at this spin here, it will be possible to write the Hamiltonian in terms of the total spin if each spin is coupled to the two spins of neighboring dimers. And this is obviously not true here. If you look at this spin, for this dimer, it is okay. This spin is coupled to both ends, so this spin will be coupled to this, but it is coupled only to this spin of the dimer. So this means to be able to write the Hamiltonian in terms of the total spin on this dimer, we should add another bond here so that this spin is coupled to this spin and to this spin. And this is what I showed when we had the model with J2. So if we do not have J2, and if we try to write the Hamiltonian in terms of the sum and the difference of the spin on the dimer, the difference will not drop from the Hamiltonian, and then the model is not exactly a Heisenberg model with a total spin.
Thank you.
I think there is a question by Didier Poilblanc online. I don't know if you.
Yes.
Yes. May I ask a question?
Yeah.
So very nice talk. Very nice talk, Frederic. With many things. I would like to have to ask you a question about the J1, J2, the last part of your talk.
Yes.
So you find this Ising transition at large J2. And so I was wondering, what do you expect? It's a little bit about expectation. It's not what you would expect regarding the high temperature phase. Would you expect it to be smoothly connected to the spin liquid phase at zero temperature, or would you expect to see some transition? Because this zero temperature spin liquid phase is expected to be critical, so somehow with diverging correlation lengths. So would you expect that the high temperature phase, which has a finite correlation length, to be smoothly connected to this phase if you vary J2 in temperature and try to connect the two?
Well, first of all, I saw the spin liquid. Just to make sure. I mean, this is, I think, the only graph I have to discuss.
Yeah. So exactly. I'm talking about the zero t equals 0 axis. So there would be the spin liquid phase.
Yeah.
And
but the
how
liquid,
does it connect to? Yeah.
So I thought they were actually. I mean, I thought the current understanding was that maybe there are actually two phases here: an algebraic phase and then maybe a valence bond crystal. No,
Yes.
In the solid. So if there is a valence bond crystal, if it has four states, we expect maybe the transition to be first order. So there should be finite transition temperature.
Right, but I'm talking about really the spin liquid phase with no
with the algebraic.
With algebraic order. So algebraic correlation. So do you expect, if you go up in temperature and try to connect, make a path that goes to the your high temperature phase, would it be smooth, or would you expect a transition somehow?
I suppose it will be smooth, because we cannot have an XY Costelli-Thouless transition. We have long range order. It's Heisenberg's spin. So whether it is ordered or algebraic, I suppose the correlation length will just grow upon reaching low temperature. I suppose there will be
diverge at zero temperature.
I think it will diverge at zero temperature. Maybe not in the same way, but similar to what happens in the ordered phase. If we go in the Néel phase, we just expect the correlation length to increase as exponential J over T. And in the algebraic, maybe there will be some correction to that scaling. That will be difficult for IPEPs, because that's one thing. IPEPs is very good to local quantities, but if you talk about the correlation length, it's very difficult to go to very large correlation length, because it becomes very much dependent on chi, on the parameter of the corner transfer matrix RG. So I think it might be difficult to check the scaling of the correlation lengths at low temperature with sufficient precision with IPEPs. But my expectation is that if there is no broken lattice symmetry, since it's Heisenberg, I suppose there will be no finite temperature phase transition.
Okay, thank you.
Okay, thank you very much. We are out of time, so let's thank both speakers of our second morning session once more.